Yeah, thank you everybody for inviting me and giving me a chance to talk here. So I was asked to talk a bit about design, right? Like design choices, how we design principles of Kokkos. And so this talk is to a large degree slightly different than other talks I've given. So I don't know how many of you are familiar with Kokkos, right? What I'm not going to do in this talk is I'm not going to give you a great overview of all the features in Kokkos and stuff like that and what you can do with it, right? I really will focus a bit more in on, why we ended up with certain designs, and what the kind of thinking behind some of the principles we are following in our API design are. But, where's this all coming from, right? This is coming from the problems we saw, starting up about maybe, 12, 14 years ago. If you look back then, right, the top 500 supercomputers, like before I joined Sandia, when I was doing my PhD, right, it was all CPUs, right? You had like, Xeon and AMD Opterons and some IBM Power PCs, right? All of these were like 2-core, 4-core, whatever systems. If you look at this thing, at the top 10 computers, just like 2 years ago, it looked much more diverse, right? We have all these CPU systems, and all of them are combined in some way or form with accelerators, right? At that point, there were 4 systems in there with NVIDIA GPUs, 3 with AMD GPUs. There was the Sunway accelerator and this matrix thingy, and some other Chinese machine. And the big problem for application is, right, that these things want different programming models to program them, right? Like CPUs, you have OpenMP, threading building blocks, .thread, and stuff like that. Then on the accelerators, there was CUDA, ROCm, OneAPI, OpenMP, Offload, OpenACC. And, that meant that the world was getting more complicated. And this was something we were seeing, about 12 years ago when Oak Ridge started building Titan, that was something which was on the horizon, where it started to becoming more complicated, and people didn't quite know how to handle that, right? And this is where Kokkos came in. Essentially, our core problem was that we needed applications which could run on NVIDIA GPUs at the time and on CPU systems effectively without maintaining 2 code bases, right? We didn't have, our application teams don't have the resources to do that. They couldn't really do all the CUDA stuff at the same time as optimizing for CPU systems, etc. And so we needed a solution which could sit in the middle and do that for them, right? And that's what Kokkos is, right? The idea is you write Kokkos code and we then map it to all the different architectures. So if you heard anything about Kokkos, right, that's probably hopefully what you knew about it. And so what is it, right? It's the C++ programming model, right? It's implemented as a template library on top of things like CUDA and OpenMP and HBX and many other things. One design thing here is that it aims to be descriptive, not prescriptive. It comes from one of the design goals I'm going to talk in a little bit about. What that really means is we don't generally give people much choice, and you will see that later, right? We don't expose like a lot of like detailed decision making, right? We're trying to align with the developments in the C++ standard or influence the developments in the C++ standard, and it really replaces your usage of things like CUDA and OpenMP and HIP and whatnot. There's also other things, when you come down to it, you start having your programming model together, people start asking you for all kinds of other things. Like they ask, oh, how do I call BLAS now, right? Where do I get my sparse linear algebra functions from? Oh, do you have an FFT and stuff like that, right? How do I debug my code? How do I profile my code? How do I get that information out? All of these things are things people start to ask. And if you really want a comprehensive solution, you need to, take that into account. It is open source, maintained and developed on github.com, at Kokkos, the Kokkos organization. In fact, Kokkos is now part of the Linux Foundation. We are a Linux Foundation project, and we are part of HPSF. I'll talk about that a bit later. And we have lots and lots and lots of users around a wide range of institutions. One important misconception is Kokkos is not just for GPUs, right? The original idea of Kokkos was we want to effectively write code for both CPU systems, pure CPU systems, and GPU systems. And we still care about that a lot, right? Los Alamos, one of our partner laboratories, they have fielded a lot, as the last machine they fielded was a large CPU-only machine, right? It has like Intel Sapphire Rapids with HBM in it, and that's the only thing, right? There's no other accelerator. So we still care about this stuff, right? We care about machines like Fugaku, in Japan. It's not just for GPUs. So when we started, right, we had a few design goals in mind. One of them obviously was portability, right? This thing needs to be portable, right? Your code needs to be able to run across all the different architectures, right? What that leads to is we can, as of the functionality we're going to provide, right, must be implementable on all HPC architectures, where certain things we won't provide to you, right? Kokkos, for example, does not have the equivalent of an OpenMP critical region. That's not something you can do in any reasonable fashion on all architectures, right? It's only something you can do, halfway reasonable on CPUs. Another important thing was ease of use. CUDA programming, is still something which is fairly complicated, right? I like it, right? I like CUDA. I think it's a fairly elegant language for what it needs to do and what it was intended to be used for. But when you actually encounter a large number of like engineers and whatnot, right, who write HPC applications, and maintain HPC applications, writing the stuff in CUDA is fairly complicated, right? There's lots of boilerplate things you have to do in order to just, for example, implement a simple for loop, right? And this is something we want to avoid, right? So on top of it, we are trying to reduce verbosity by defaulting common choices, right? If there's something, almost everybody will do immediately, right? Then maybe, you don't need to express that explicitly and we'll just do it for you, right? Performance is critical, right? What that means is we only expose functionality which can be performant. And more importantly, we restrict semantics of what our functionality in a way that, allows us to get performance across all architectures. And we're going to see some more details on that in a bit. Another big design principle was that we wanted to prevent and detect mistakes of users, right? We want to make it less likely that you shoot yourself in the foot. That leads to choices such that, we have very strongly typed interfaces, right? We have a lot of our interfaces or classes and so on have invariances, right? Where you can't, you can construct it, but after that you can't actually change certain things anymore. We implement restricted semantics, semantics which make it harder to make mistakes. And a lot of our things have like checkable properties, right? Which essentially enable us to detect like violations of our semantics or at runtime or even compile time. And the last thing was aligned with the C++ standard. That was something we considered from the beginning. Essentially, it means, you want to avoid inconsistencies with the standard and you want also to work on getting widely used features into it. Okay, so this is the 5 things we kind of, set out to try, right? We want portability. We want it to be easy to use. We want to do it all in the way that we can get performance out on all these architectures and encourage people to write their code in a way that we can get performance out. We want to be able to prevent and detect mistakes, and we want to align with the C++ standard. What that led to is something we call our 6 Kokkos core abstractions, right? We have abstractions for parallel execution and data structures, and essentially all our kind of concepts fall into these kind of 6 buckets in some way or form. On the parallel execution side, right, we have one thing we have is execution spaces, and this is one of the things where we come in with this strongly typed thing, right? These execution spaces are largely types, right? Things like Kokkos CUDA, Kokkos HIP, Kokkos OpenMP. And what we express is where code runs, right? And what kind of execution resources are available to it. What you do with that is you combine them with execution patterns. So all your algorithms need to be written in these patterns, in like, parallel for, parallel reduce, parallel scan, right? And these express, loops and certain kind of dependencies between loop iterations, right? And the parallel for, it means that nothing has any independency between iterations, right? Reduces that every iteration contributes to some common result in a well-defined way. Scan is, the prefix scan or a postfix scan, right? And so on. And the last piece for parallel execution is the execution policies, and that's essentially how you execute. You go from 0 to n, right? You have maybe dynamic or static scheduling. Things like that. Then we have the data structures, and that has the kind of like commonality to the other side. Whereas the memory spaces, that's again types, which strongly say where is something stored. And execution spaces and memory spaces will know about each other, right? So execution spaces know which memory spaces we can access, and memory spaces know which execution spaces can access them, right? And you can check that at compile time. Another important thing was memory layouts. That has mostly something to do with performance, like, how do you store things in memory? How do you order things in memory? And then memory traits is kind of how you access things. Do you do atomic accesses? Do you do streaming accesses? Things like restrict, etc. Breaking it down in these concepts really helped us kind of clarify a bit, and keep kind of a track through the zoo of things we can do. So the first thing you're going to start with, right, is parallel loops. If you think about HPC code, right, like most of it at its heart, right, has some kind of for loops, right? That was what, everybody writes somewhere, right? Do something for every index in a range, right? Classical thing. For int I equals 0, I smaller n, I plus plus, do something. All we need to do is we need to do that in parallel, if we want to have any hope of exploiting GPUs, right? You can't use a programming model like stud threads on GPUs, right? You won't like launch like independent 100,000 threads, right? You need some way of getting concurrent work out in a very concise description, right? And the parallel loop is that. And so the basic concept we said is, okay, we want to write parallel for, we give you how many loop iterations we have, and you give us a functor or lambda, right? In this case, lambda. And that lambda takes an I, and then you do your loop body. There's a parenthesis missing at the end here for those of you who know C++ syntax well. But yeah, anyway. This is kind of, if you look at this expression of a GPU, right, it demonstrates a bunch of these design principles, right? The ease of use thing, this is really, what I wrote there for this parallel loop, right, is really the minimal necessary information we need, right? It says we should do something in parallel, right? Parallel for. It gives us the iteration range, and it gives us what we need to do for each of these iterations, right? The loop body in form of this lambda. The portability here, or the one thing, which really is important here for portability is this Kokkos lambda thing. That hides function markup and some other things I'll talk about on the next slide. And then the design principle for performance, right, is something which is a little bit hidden here. When you read our documentation, we're going to tell you that this parallel for doesn't promise you anything, right, in terms of order of execution or concurrency. So we don't tell you really how many threads will concurrently work on this. We won't tell you in which order these iterations, 0 to n, will be done. And we definitely don't tell you how these iterations are mapped to threads necessarily. Right? And what that allows us to do is it allows us to make optimal choices for how we want to map this to hardware. And it prevents our users from doing something which would be hurtful for performance, right? if we don't guarantee any type of order of execution, right? You can't, it means you can't have like loop carried dependencies or something like that, right? It would be illegal to write code that has these kind of dependencies between iterations, right? Not promising order of execution or concurrency also means a user can't implement their own synchronization mechanism, right? You cannot write a spin weight loop here because you don't know, right, that anybody else that anybody else will actually execute and get there, right, and unlock you again, right? We don't give strong forward progress guarantees, right? We don't tell you that, every thread which is active will make any kind of progress and so on. And that is actually really key to performance, right? What a lot of parallel code makes it, non-performance portable is that you write algorithms or use kind of synchronization mechanisms which work well in one kind of concurrency regime, but not in another. And so our semantics of this simple loop, right, prevent you from doing that already. Now, what actually happens, right, in this thing is a bit more complicated, right? What this thing before actually translates to is a parallel 4 with a label, because you didn't give us a label, we auto-generate that. And the range and the simple n there is actually a shorthand for a range policy. And specifically in this case, it's a shorthand for a range policy which executes or says that it's gonna execute in the default execution space. It's using an index type which is derived from the default execution space's memory space. And it executes in the default instance of the default execution space. And because you just gave us an n, it actually says I'm going from 0 to n, right? All of this information was implicit or defaulted, right? There is a begin and end. It actually just giving us n actually means 0 to n. But it turns out, yeah, there is a lot of loops, right, which go from 0 to n. That's, I don't know, probably the 80% choice, right, for loops. Even though you didn't see it, where you execute is still strongly typed, right? There is a default execution space. And even though you didn't explicitly express that, that was a default choice which was still there, right? Not telling us anything doesn't mean we're going to randomly choose where to execute. It just means we're going to explicitly use the default execution space. That type is also associated with a default queue, right? That's what this default constructor here does. It actually gives you the default queue of that execution space type. It's kind of like in CUDA, the default stream, right? We also, explicitly define here, what is the iteration index type, right? That thing is strongly typed. It's 32-bit versus, 64-bit. You can choose that if you want to manually do that. And we internally can check that, right? If you give us a number here which is too large, we will be able to check that. And in fact, the way we do that is we take this thing not implicitly as this size type, we actually take it as whatever type it is, and then we'll do a conversion safe check whether it's in range, right? So if you give us a 64-bit number here, but your size type is only 32-bit, right? Then we will do that comparison in 64-bit, whether it exceeds the allowed iteration range. And maybe the most important thing we hit here is in the Kokkos lambda, and that is this capture by value. That is actually fairly critical. And I'll talk about that in a little bit more. So what you saw here is, right, this thing is actually fairly complex, right? There's lots of information here. And if you tell a user, if they first time encounter Kokkos, oh, here's all the things you need to define, right? You need to give it a label. You need to define an execution space. You need to define a size type. You need to define, what queue it's coming from. And you need to have all this markup here you never heard about if you haven't done CUDA, right? That would probably be bad. What we are really doing, right, is we give users the ability to be more specific when we need it, but by default, right, we make kind of the common choices for you, right? And that's where we started with this parallel 4 and functor, right? Which really is, your range policy in the default execution space going from 0 to n. You can give it an index type, right? And again, what this means is you left the execution space out. So it's the default execution space. You only provide the information you want to customize. You don't need to customize everything if you can't customize anything, right? You can do things like, set chunk sizes, etc., right? There's endless things you can do. You can do things like desired occupancy, right? That's something where on GPUs we control, how many threads will actually be active. Essentially, what that can do is it can increase the amount of available L1 cache per thread. If you artificially reduce how many threads you're actually gonna have in flight, and for some codes that can do like 2 to 4x performance improvement over just running, all the threads at the same time. So the basic point here is, right, we make the simple things simple, right? If you don't know anything about all these other things, right, how to set a chunk size, what kind of occupancy you might want, what index type you should use and whatnot, right? We're gonna default all that for you. But if you need to define it, you can define it. And you can define it by just providing the information you want to define. One thing which is mostly hidden from people, right, is this Kokkos lambda thing, right? And what that really does is it helps a lot with correctness. And one important thing was what I said was capture by value, right? Let's assume you could let users capture by reference, right? You could capture by reference, and you write something like this, a function foo, which gets like some reference to an integer and a range, right? And you sum up, into that thing. Now, this code would have a lot assuming it works, right? And on CPUs, this would compile, right? Kokkos PerfLab, where you would do this on CPUs, would compile. If you don't, where we actually have some experimental tools which would detect that this is wrong, but in principle, this would compile. But it has a lot of issues. The first one is you have a race condition on the update of A, right? You captured it by reference, everybody has the same reference, and every thread will try at the same time to update that thing. So you have a race condition and you lose contributions. The next thing is PerfLab actually in our semantics is asynchronous, right? So this function call will return before that PerfLab is potentially done. Now, A may exceed its lifetime, right? May exceed the lifetime of a PerfLab, and you're now updating into invalid reference. And if you actually try to compile this for GPUs, right, and assume it would compile and work, accessing A is a memory access fault, right? A is probably some like local temporary variable in the stack of a CPU thread. And the GPU can't access that. It will, segfault on that. So if you now replace that capture by reference here with Kokkos lambda, this code will actually not compile. What we do internally is, first of all, it will capture by value, right? So it will make a copy of A. So even if it were to compile, you wouldn't actually get the result back, which would already be a problem. But we treat the lambda as const, so you can't modify A. So this thing will not compile because it will say, I can't update A. A is const. A is non-modifiable. So we catch that mistake, right? That mistake where you try to just randomly access something and modify it and lead to problems. Generally, raw pointers are to be avoided, right? Naive implementation of a matrix add, you look at that, right? You have like this int n, int m, and the double star, A, B, and C. And so this would be like typical code you could write with this, right? And this would actually be legal code in C++, right? In Kokkos, you can write this, right? You write this thing, you do the outer loop over n, you do an inner loop over m, and you calculate your index, into the array, and you sum this up, right, for a matrix set. But there is a bunch of correctness concerns, right? How do you know that A, B, and C actually are representing n by m matrices, right? How do you know that that they are all the same length, right? That it's associated with this n and m, right? That the caller didn't make a mistake. Is the storage order of A, B, and C, the same, and the one we assume, right? This index calculation here essentially says, we have a very specific storage order here. Can the default execution space actually access A, B, and C? Is the lifetime of A, B, and C guaranteed to outlive the runtime of PerfLab, right? Who knows? Now, the way we're going to solve that is we solve it with Kokkos view, right? And what we found is, right, that we need at the fundamental data abstraction, we need some kind of like, smart pointer-like thing which represents multidimensional arrays, because, it turns out in engineering and science we have a lot of multidimensional arrays. Fortran knew that for a long time, which is why their basic data structure is a multidimensional array. But we need to go a bit beyond what Fortran did, right? For example, we found that it's really helpful to have both runtime and compile time dimension, and that you can mix them. We need to do things like subslicing. We need to be type safe with respect to allocator, right? So we want to know where this thing lives. And we need to be able to reason about data layouts. And that's where view comes in, right? View is templated on a data type, a layout, a memory space, and memory traits. Really, this is actually not the C++ declaration of the class. It looks slightly different, more complex, but it gives over the gist. And one thing we did here is, again, we defaulted choices, right? The same as what we did in REPARAL 4. You can only give us the information you actually need. At a minimum, that means you give us the data type, right? I want a, n by m by 4 array, so double star star 4. You can construct that, you have to give it a label, and you have to give us runtime dimension. You can explicitly tell us where this thing is stored, right? Which memory space it's in. If you don't tell us, it's going to be in the default memory space of the default execution space. You can explicitly set the layouts, right? Layout left versus layout right, Fortran versus C layout, and so on. But again, the same principle here, right? You can give us only the information you want to specialize. Otherwise, all the rest is having some type of default. It doesn't mean that it doesn't exist, right? Not specifying a memory space doesn't mean that it's type erased with respect to memory space. It just means the default memory space is used. And what it prevents is it prevents a lot of correctness issues. If you look at the matrix add, you don't actually give it an NMM, right? You just give it the 3 views. And these guys know what their length is, right? You get the N and M out of the extents of one of the views. But what you now can do is you can actually check that B and C have the same dimensions, right? But the 2D arrays you gave me here were actually meant to be, of the same size, are the same size. Because it's 2D arrays, there's no explicit index calculation done by you, right? You index into it with I, j, which means, and that works because the storage order, the layout left, layout right, and whatnot is part of a view. So even if you were to pass in more complicated things here, right, and be not as restrictive as I'm in this small example, if these things are different storage order, that isn't actually a problem because you operate in logical space, index space. There's a memory space hidden here, right? You can't actually pass mismatched views here in this case because all of these are expected to be default space. If you compile for GPUs, that means you can't pass a host space thing to it, right? It will essentially tell you this is an incompatible memory space. This doesn't work. Even if you were to, relax the restrictions up here a bit, in the signature, when you actually try to access that in the parallel 4 with default execution space and it can't access it, it will actually error out with saying, I can't do this, right? This is accessing the wrong memory space. And on top of it, these views are reference counted. And when they finally deallocate, we actually will block all outstanding asynchronous work, which means, work which you have started on any of the allocated data from Kokkos will finish, right, before any of the allocations go away. And that's all safety features which make it much less likely that you run into trouble, right? One thing, right, I said earlier, these layouts, right, are something which is really important for performance. If we go back to the raw pointer version of this, there was actually 2 choices how you could have indexed into this matrix, right? You could have said I times m plus j, or you could have said I plus j times n, right? And sure, you could write this thing differently. You could multiply n by m because I'm just adding these things, right? And just do a flatten out the loop. You could actually use a multidimensional range policy, which indexes over 2 things. But let's say we keep this, right? What you see when you run this code on NVIDIA GPUs versus like CPUs, right, is that for GPUs, you really want to do this Fortran layout index calculation, while on CPUs, you really want to do the C layout index calculation. And that has really something to do with, caching versus coalescing. And our tutorials talk a lot about this. Basically, what that means is on GPUs, right, adjacent threads wants to do coalesced loads, right? You want to hit the same elements on the same cache line. On CPUs, threads, rely on prefetching and whatnot, right? And you don't want to share cache lines. So every thread needs to hit like different cache lines. That's really, and you want its next access to come from the same cache line. That's really what's at the core of it. But basically, even with simple example, what that shows is optimal storage order for an algorithm depends on the architecture. And that's why we have this layout left versus layout right? And what I didn't tell you earlier is that if you don't specify this, your actual layout depends on what you're compiling for. If you compile for GPUs, we actually default to layout left. If you compile for CPUs, we default to layout right. And this is Fortran versus C layout, which means if you parallelize over the leftmost dimension, we give you the good access pattern by default. Right? Again, something hidden from the user, and one of these things where we default things. On top of it, we do a lot of other things, right? We have this, one of the things we really started doing is we started to hide away a lot of problems from, or solve a lot of problems before it hits our real applications, right? What that means is we work and collaborate with the vendors on the application's behalf, right? We work with them on co-design, things like we worked on AMD GPUs since 2014, right? Long before they sold anything for real in the HPC market. We work with them on improving the software stack, right? Like, for example, Kokkos with Kokkos Test Suite is part of a vendor CI for some of these vendors, right? They run that as part of their compiler tests, etc. We hide a lot of things from you don't want to know, right? Things like Clang versus NVCC device markup, right? They have actually different overload resolution rules, which make a lot of things complicated, right? The Volta thread model broke a lot of CUDA code because it was relying on implicit synchronization. But because we don't allow you to write your own synchronization mechanism at all, right? We implement them all for you. You will never know that, right? Because we solved that problem for you before you ever try to run on these architectures. There's lots of details here. We don't need to really talk about it, but that is really another thing, right? We try to hide a lot of this complexity from our users so that they don't need to think about it, right? We tell them what you need to think about is you need to just think about how do I expose all the parallelism I have, and how do I write code in parallelism where I'm not allowed to know, how many threads do I have and, which order stuff executes in. And by doing that, we get the freedom on our side to implement it in the right way on all these different architectures. With getting into C++, right, that's something, we said we want to align with the C++ standard. I can't go into too much details here, right, how, a lot of our designs, kind of try to align with that. But we also try to get things in, right? And one of the big successes we had was in C++ 23, we introduced mdspan, which is, multidimensional arrays for C++. And that really mirrors what Kokkos View does, right? We have this element type, expressing what data is stored. We have the extents, which is the runtime and compile time extents. You can mix these things. We have the layout and we have the accessor. And when you look at how the stuff maps, right, it maps slightly different, right? The data type is actually a combination of element type and extents. The layout is exactly the same thing. And the space and the memory traits in Kokkos View can be expressed with the accessor. We are currently working in Kokkos to replace basically all the guts of Kokkos View with mdspan. And that works because it was designed to express, be able to express all these things. And the nice thing is now we do that in a way which is really, really, really well specified, much better specified than any of the Kokkos View things ever were, right? Because getting it into the standard means you have to write a lot of really exacting correct words. And that has a benefit to everybody, right? Because you now get in some ways, much, much better documentation. And also you get very well-defined customization points, to do more special things on your side. You could do a lot of this customization with Vue, but it was complicated, and you actually had to go into the guts of Kokkos, right? You had to specialize certain impl features, and we really didn't like to see that. Now you have official points to do that. So the last thing is, right, what's really important to get this also success, besides getting the design principles correct, is you need to build a community. And that takes time, right? Kokkos didn't come out of nowhere, right? We started working on this. There was actually a Kokkos before the Kokkos, which was mostly focused on linear algebra, which started, all the way back in 2003. And when 2006 GPUs showed up, and we knew that in 2012 that Titan was going to be there, right? I mean, that was decided in like 2009 or so. And that's really when in 2010 we started with Kokkos array data abstraction. When we worked on things like LAMMPS and Trilinos, but we already worked, in 2013 on AMD APUs, right? There's all kinds of stuff which happened, right? We got Trinity, we got with KNL, we had the NVIDIA GPUs and IBM Power combination, right, with Sierra and Summit showing up, and so on, and then eventually AMD GPUs. And throughout that, right, we really started, working with our applications. And one of the things they told us, right, what matters to them is they really want to use the tool chains from the vendors. We had to support XL and stuff like that, right, because they wanted that. And this is something, where doing all of Kokkos as a library on top of the vendor tools was really critical, right, because they absolutely needed to be able to run the vendor tool chains, which means Cray compiler, Intel compiler, XL compiler, and whatnot. We couldn't just use LLVM and GCC. I want to leave a bit time for discussion, but what that led to is, right, that in the DOE exascale computing project, eventually, a majority of C++ codes actually ended up using Kokkos, and a large majority used something which is, Kokkos-like. There's these other two things, AMRX and Raja, which are also C++ abstractions, right? And of all the C++ codes in the DOE exascale computing projects, right, 33 out of 39 used one of these abstractions. And some of the rest didn't even run on GPUs because they didn't need to, right? They were like IO libraries and stuff like that. Of these 6, by the way, only one uses OpenMP offload, right? ECP really helped us expand, right? It helped us expand to more developers, right? Like with Oak Ridge and Argonne and whatnot getting involved. And it helped expand our user base. And what that led to is what was really critical actually was the Slack channel, right? That was really helpful in doing user support. And what we see there is we have people from over 150 institutions in there. We have, I don't know, we probably have about 1,700 registered users right now, or 1,800 or so. And about a third of those are Department of Energy, right? The rest is other stuff, universities, other institutions, etc. Now, the last puzzle in the game is something we recently did. We always struggled a bit with convincing people to contribute to Kokkos, right? In particular, in the beginning, it was kind of seen as, oh, this is a Sandia project, right? How do we know that our contributions aren't, disappearing at some point because you decide to do something different, right? Or how do we know that we have influence on this? And then later we got a similar question like, oh, this is a DOE project, right? How do we know that, us contributing from non-DOE land will have impact on this project and, be a true partner, right? And so one thing we recently did is we joined the Linux Foundation. And within that, we helped found the High Performance Software Foundation. So it's an umbrella organization for high performance software in the Linux Foundation. And we joined it together with a bunch of other things, like there's Spec, for example, in there, there's Trilinos in there, HPC Toolkit, and so on. And what we really try to do with that is we try to establish open governance, make this true community projects, make it easier for other people to justify contributing to it and feel like we're true partners, right? And not just somebody, some random DOE people graciously let occasionally put in a pull request, right? We want to partner with people. And what that means is we gave up certain rights, right? We transferred the trademark of Kokkos to the Linux Foundation, right? We wrote like governance documents, right? How the governance of this thing is gonna work, right? We are willing to give up a degree of control over the project in order to build a community, right? And that is really important, right? You have to be willing to give up some control. That was already important in expanding inside DOE, right? I gave up some control to Oak Ridge, right? When I got these developers involved. And that's something you need to be willing if you really want to do a community project. And we hope that, HPSF is gonna further that. We have some European partners already. CEA is in there. CEA has a governing board seat, actually. CEA is also a big partner now in Kokkos, right, contributing to it. We hope that other institutions are joining, like Jülich and CSCS and whatnot. And we really want this to be, like a place where the community, the HPC community comes together and collectively develops these pieces, these central pieces of code, right, of software technology. Because the amount of work which goes into do something like Kokkos at the level where we do it, where, thousands of developers from hundreds of institutions can use it reliably. The amount of work going into that is extreme. The amount of like software engineering time you have to spend on this to get this, really reliably working is fairly substantial. And it's something which I think goes beyond each individual institution. And by collaborating all together on this, I think we can come up with a better solution, have a better experience for all the users and get synergy effects like, that vendors are interested in supporting it directly because there's enough user base there. And so, if you want to get involved, we are starting this up right now. The working groups aren't formed yet, but we are starting to form those now. I think at supercomputing, maybe we will have, a first couple of these ready. If you're interested in collaborating, right, in some form, let us know, and I can get you involved. We got lucky. I have to admit that, right? We started this project at the right time, at the start of the accelerated computing era. We started it at the right place. Sandia has mission codes, right, which needed to run on GPUs and CPUs. We didn't have a choice, right? We needed to do that. But we also made a bit of our own luck, right? We really cared about user concerns, right? We made it easy for them to use this, right? But we are not involved, right? We made it productive for them to use that. And we really, really, from fairly early on, tried to build a community, right? And all of these things were critical to making Kokkos successful. And with that, I'm done. And I think we have some time to do a little bit question and answers, huh?
Yes, we do. Thanks a lot for this very insightful talk. All right, so if there's any comments or questions, please raise your hand, put it in the chat. If you want to raise your hand and speak up, I can call you in order or write your question in the chat. Okay, I'm going to start. You talked about patterns at the beginning and how Kokkos is organized around patterns. So how extensible is that kind of framework? Is it like a rigid thing and I have to force my algorithm or my implementation into those patterns? Or is it possible to extend patterns and write your own patterns? Is there like a guide that helps me do that?
So no, the patterns have to come from Kokkos, right? The core patterns have to come from Kokkos because the core patterns are architecture dependent, right? How you implement the reduction depends a lot on like how much concurrency there is, how the access modalities are, what kind of synchronization mechanisms the architecture has, and so on. But so Kokkos has now an algorithms library, right? And that provides a lot of like the C++ standard algorithms, right? Like the transform, reduce, and all these other things, which are there, the find, and I don't know. There's like 70 algorithms or something like that. But it turns out that the vast majority of these large number of algorithms can be expressed or can be mapped onto the three fundamental ones, which is the parallel for, the parallel reduce, and the parallel scan. A lot of other things can be expressed in terms of these fundamental building blocks, where some which can't fully be done like that, but most of them can, right? And so what you do in the end is you build higher level algorithms on top of these fundamental patterns. And that's really where this is coming, where we are coming from, right? And what Kokkos core does, right, it's providing these fundamental algorithms. And when some other libraries, right, like people, at a higher level write like other patterns, right? Like for example, there is a number of libraries out there in finite element codes which don't give you a parallel 4 over indices, which give you like a for each element, right? For each element loop over all the neighbors of the elements, right? All the kind of connected pieces and stuff like that, right? So that is something you definitely should do. But in the end, you need to express it all in these fundamental patterns, and those are not really that extensible. I think we have a good theory of why, these three patterns are kind of the fundamental piece. There's some other things, like, for example, there's a static task work graph, which isn't used widely, but which can express certain other patterns. But again, we need to implement that at the core level, right? Because the fundamental patterns are super architecture dependent, right? And that's not something you as a Kokkos user can implement.
There's a question in the chat, actually two that belong together. How does Kokkos compare to SYCL? And somebody mentioned that somebody postulated that it would be possible to build SYCL on top of Kokkos or vice versa. So what's your opinion on that?
So there's a couple of interesting points here, right? Or thoughts here. One is do you really mean SYCL or do you mean one API, right? Because the only real good implementation of SYCL is really one API, right? Now, how does it compare? I would say originally, right, SYCL wasn't actually enough to implement our applications, right? It wasn't enough to implement Kokkos. And I was actually on Intel's initial advisory board for one API to help them, fix that situation. So SYCL is still a little bit, in some places, a little bit more verbose than Kokkos by default, right? There is certain patterns in SYCL which you could use if you write your code certain ways, like the buffers and the data dependencies, which is something we don't have. But it turns out that we introduced, the what we call USM, the thing where you can actually have pointers, because the data dependency stuff has a lot of problems if you try to write C++ code. It's fairly technical why, but effectively it doesn't really work for class-based applications because the buffers can't be accessed directly, and the accessors have lifetime, which essentially only is the dispatch scope. And so you need to regenerate them, which means that at the point of dispatch, all the data members need to be public, right? You can't do like implementation detail data members anymore, which is a real big design problem if you want to use this. All in all, right, SYCL is probably fairly close to Kokkos otherwise, right? It has similar patterns, right? There's parallel force, there's reductions and stuff like that, right? It has some of these concepts for data storage, right, and whatnot. The one interesting question is, at this point, I would say it's a fairly safe bet to bet on Kokkos getting more long-term support than one API, right? If you look at the news for Intel, how they are scaling back their GPU business again and their AI business and whatnot, right? The rationale for them really supporting one API, it's not clear that it's still there. You don't need one API for writing CPU code, right? For x86 for the CPUs, right? So are we going to support that the way we have supported that over the last few years going forward? I don't know. And none of the other big vendors are, right? So neither AMD nor NVIDIA are officially supporting SYCL in one form or another, right? That is a big difference, right? The big difference here is that Kokkos is essentially vendor independent led, right? We collaborate with vendors, but the leading institutions are not vendors. And the leading institutions have an interest in providing a vendor neutral solution, right, which works everywhere. So I think that's a big difference.
Another question, suppose I have a modern Fortran code that I want to run on HPC architectures effectively, and we want to use Kokkos for that. How would you recommend going about that?
Fortran is a perennial thorn in our side, right, in some ways. Fortran is actually a really nice language, right? For engineering and science codes, right? It's a really nice language. I mean, it was developed for that, right? The big problem I see for Fortran, right, is the general support, right, in the vendor community. There's essentially absolutely zero synergy with all that AI wave stuff going on, right? Which isn't and there is synergy, right, on the C++ side, right, because we use the same programming models to implement the AI stuff, right? We use C++ there and whatnot. We use CUDA and HIP and etc. So that's the big problem, right? Now, if there is actually an argument to be made that if you trust, the OpenMP offload compilers or the OpenACC compiler, and you can restrict yourself to just the vendors, which support that, then that might actually be not a bad choice for you, right? So it fits better into the Fortran world. But if you can't do that and you're not willing to do that, and it turns out that within DOE most codes aren't doing that anymore, then the way we are going about that is that people leave in particular at Los Alamos, for example, they leave kind of a framework in Fortran, and they then port individual kernels over, right? And with modern Fortran, right, it's fairly easy to have these descriptors of your arrays and then have a function which essentially just creates an unmanaged Kokkos view out of your descriptor, right? And that means you can alias the data fairly easily, right? And because Kokkos can express, layouts, right? You can express Fortran layouts, right? You know that this is a Fortran array, right? You see that as the same multidimensional array on the other side, and so on. If you then combine that with stuff like potentially, allocators which allocate in kind of, or where you're allowed to access the data on the GPU as well, right? You might even get rid of some of the manual data transfer all the time. If you're on something like MI300A from AMD, that problem goes completely away because all the memory is just an HBM memory, and it will just work, right? And on those kind of platforms, also things like Grace Hopper, it actually is fairly efficient, right? There's relatively little penalty for doing this kind of back and forth there. And so Los Alamos has found reasonable success with that, right? And they are doing that for all their mission codes, right? Los Alamos has been a Fortran shop, long time. It still is. And recently, their entire mission codes decided, as of a program, they decided to go finally for real with Kokkos. One of them had already done it, but now the rest of the program is following suit. So they are committed to that, and they are going down this way, right? And if you have more detailed questions on that, right, come to our Slack channel, and we can connect you with some of the Fortran people at Los Alamos, right? And we are doing that now all the time.
All right. Next question, does Kokkos support hybrid CPU-GPU execution of its kernels? I mean, you compile for a device, right? So can you do for both?
Yes, I mean, what you saw there is, right, that our execution is type safe, right? As I said that, when you execute something, a kernel, you explicitly define where to execute that, right? So what you can do is you can launch asynchronous kernels on the GPU, and then also launch a kernel on the CPU, right? You can have OpenMP and CUDA as backends at the same time, right? You can have HIP and stud threads at the same time, right? You can have, for that matter, CUDA and HBX at the same time. And if you do
select that on a kernel by kernel basis.
But you select that on a kernel by kernel basis, right? And it's strongly typed, right, to do that. So what we don't support is we don't support something where you say, oh, I have this range of 0 to n, and I want to use both the CPU and the GPU at the same time to execute that range, right? And split it in some way. That is something we don't support. There was a time when people tried that quite a lot, like in the early 2010s, that was, there were a lot of papers written on that. And we actually had some code which could do that, right? Where it auto-tuned, like how much to do with CUDA and how much to do with like the CPU side. And it turned out that the auto-tuner always came back with a 1.0, right? Do everything on the GPU, or do everything on the CPU for that matter. Because the coordination effort and the kind of data transfer and data coordination effort between CPU and GPU generally would the overhead of that would exceed the extra benefit you get from using both sides. If you think about it, right, even on the modern systems, your bandwidth if you have two GPUs per one CPU, right? Your aggregate bandwidth on the GPUs, is an order of magnitude higher than what you have on the CPU, if not more than that, right? Like even if you have like one GPU and one CPU, right, you're already at an order of magnitude, right? If you have like a 3 terabyte a second H100 there and a 300 gigabyte a second CPU, right? Whereas 10% of your bandwidth is on the CPU, and the same is true for compute, right? Less than 10% of it. So if your overhead of coordination, makes your code slower by 10%, you lost all of that benefit already, right? And so that's why we haven't done anything of that and are not supporting that.
All right. Well, last question, because we're almost out of time. There's a question about tools. If I want to trace or profile a Kokkos application, does it expose instrumentation? And how do we do that?
Yeah, so Damien already said, as Damien is actually my Oak Ridge co-lead for Kokkos Core. We have native instrumentation inside of Kokkos. That is always on, right? So that instrumentation is not something you enable at compile time or so. It just exists in your runtime, also in your release build. And you can hook up to that instrumentation with tools, right? There's this Kokkos Tools project, which has a bunch of things, where it can tell you, what kernels you ran, how much time they took, how many data transfers did you do and whatnot. You can write your own tools. This instrumentation interface, right, is just a C interface. And what you do is you implement that interface, you build a shared library, and you tell Kokkos to load that shared library at runtime, right, when it initializes. And so you can write your own tools. And some of our application teams do that, right? They write specific tools for their application, which, gives them data in a way they like, right? And then there's some like third-party tools which actually implement that these hooks on their own, right? If you have like Tau or HPC Toolkit, for example, I think both of them implement the Kokkos hookup, right? And so you would get that information by default. In fact, I just heard that the next version of the AMD tracer and profiler does implement the Kokkos tools. And so if you tell it, I'm running Kokkos code, there's a little flag to do that. Then it will use the labels you provide to our parallel force, and the data and whatnot will then show up in the profiling data from presented by AMD. So yeah, that's the stuff we use, right? We start with the simple tools, and then we go to something like Tau and whatnot, right? Or the NVIDIA tools, and they can get some of the information out of of Kokkos too, right? Even if they don't know it, like for the NVIDIA, for example, we have the little shared library which implements our instrumentation and then maps our instrumentation to NVIDIA's instrumentation, right? Or to Intel's instrumentation. And that way you can get that information also into like Nsight or NSYS and VTune and stuff like that.